sort of final discussion on the computational considerations. So, this is the first question that will come to you, right. So, whether you take the surface integral approach where you have to discretize finely over here, or so this was surface, or you take the volume where you have this grid over here, right. Now, how do you know whether you have grid this, whether how fine should you make DL? How would you approach this problem? So, let us say you studied these two methods, you coded them up and you got some solution. How do you know whether you chose a DL to be fine enough or not? That seems to be an important question, right, because if you choose the wrong DL, if you choose it to be too coarse, then you are not representing the fields correctly, it is too coarse. So, you will not get the right answer. On the other hand, if I make DL very fine, I will get the correct answer, but it may take me 10 times more time on the computer than I should have spent on it. So, how do we know whether we have reached the correct answer for DL? Think about it. Again, this is a common sense question. How would you figure out?
Keep running the code until you get similar values.
Yeah. So, okay, he's saying keep running the code until you get similar values. Yeah, so that is the idea of numerical convergence, that is the formal word for it. So, numerical convergence. So, what does that say? It says that, let us say on this axis I have values of DL, okay, and what do? Let me take one position over here of the where I am calculating the field. So, keep this fixed, okay, and keep changing. So, let us say I am plotting E at received point, keep plotting it, right. So, this is let us start with large values and go to finer values, right. So, DL is starting from a large number and decreasing. So, it is a sort of inverse, you can think of this as 1 by DL or whatever, but basically start from a large thing, right. So, you might actually observe some fluctuating behavior like this. Eventually, what will happen is that you get a stable answer over here, right. So, this fluctuation is purely numerical. Why? Because you are not actually solving a real physics problem, because you are not representing the fields with sufficient resolution. So, you are solving some system of equations, you are getting some solution, it has no real physical meaning. So, you might find sometimes the fields are increasing, sometimes they are decreasing. As you begin to approach the required fidelity for representing the solution, you will find that the fields stabilize like this. So, what should you do? You should look for this point where it has stabilized and say that this is the correct value. So, in any code that you write in computational EM, you should have done one numerical convergence test, okay, and typically not just for one point, but for a few points. Why? Because it could happen that by mistake you chose a point which is actually a field node where the field value goes to 0. Then you will keep thinking that how is it that my code is giving, I mean that is also valid, but you might wonder if there is something entirely wrong with your code that is giving you 0, right. So, pick a few points and it should converge, and then that is your value of DL, okay. Now, people have done these tests a lot, right. So, there is also a rule of thumb over here that you pick your DL to be in the range of lambda by 5 to lambda by 10, right. So, this is DL in this case. Picking it in this range gives you it is a rule of thumb, it may be wrong or right, it depends on the object, but in general if you have a sort of well behaved object, choosing it between lambda by 5 and lambda by 10, lambda is the wavelength of the incident field, right. So, lambda is incident field wavelength. This is sufficient to give you a reasonable answer. You can even go all the way to lambda by 15 depending on the problem. Okay. So, this is fine and this is coarse. Okay. Right. But I mean, just use this as a rule of thumb. It may be wrong also for your problem. You should check. Okay, this is just to tell you to not start from dl equal to 2 lambda or some ridiculously large number like that. Okay, that is for sure not going to work. And choosing lambda by 100 for sure is not a overkill. You know, like inside the medium. Yes, that's a good point, right? So these are values of lambda which are inside the medium, right? So what do I mean by inside the medium? So lambda is equal to lambda naught by
In V1 or depending upon V1 or
the object, typically V2. So n is the refractive index of object, right? Okay, so what is the sort of conclusion of this is that if I have an object with a very large dielectric constant, very high refractive index, I need to grid it finer compared to, let's say, a very shallow refractive index. Okay, so so the same object may need a better discretization if it had a higher refractive index. Okay, so that is something to keep in mind. Okay, so that's to summarize over here. That's what we did. We looked at the sort of differences between surface and volume, found out the RCS, and spoke a little bit about computational considerations. So for reference, I think chapter 1 of Peterson's book on CEM, he gives you this radar cross section and the approximations required quite nicely.